Hello, AP Statistics scholars. Welcome to 6.2c, Combining Continuous Random Variables. We learned these formulas for our discrete random variables, but they hold true for all random variables, even continuous ones. So remember, when you're adding two random variables, like t equals x plus y, you add the means to find the new mean, and you add the variances. When you're subtracting two random variables like d equals x minus y, you're subtracting the means, but you're still adding the variances. And that formula for variance will only work if x and y are independent random variables. In other words, they have no effect on each other. And this is very important that you continue to remember. Sean Bean says one does not simply add standard deviations, a very common mistake in this chapter and beyond. So remember, you can never add or subtract standard deviations. You can only add variances and then find the standard deviation from the variance. So just to remind you, he's got his hand like there. It's in the shape of a sigma, so one does not simply add standard deviations. Random variables with normal distributions. So we've talked a lot about discrete random variables. Now we're going to talk about continuous random variables that have normal distributions. So if you have a random variable with normal distribution and you have another one that's also normal, if you add or subtract those two continuous random variables that are normally distributed, then the resulting distribution will also be normal, and the mean and variance will follow the rules that we previously discussed. So here's an example of a continuous random variable with normal distributions. So you have two values, scores on the ACT, follow normal distributions, and females have an average ACT score of 19.6 with a standard deviation of 2.3. Males have an average ACT score of 19.2 with a standard deviation of 4.1. Suppose that we randomly select a female and then independently randomly select a male and record both their ACT scores. What is the probability that the randomly selected female scored at least 2 points higher than the randomly selected male? So here you can see those individual normal distributions. You can see the reddish colored one is the distribution of female ACT scores, and the blue one is the distribution of male ACT scores. So the distribution of female and male ACT scores have a very similar mean, but the standard deviations are way different. The male scores tend to be more spread out with a higher standard deviation. So let's think about this situation and how we would answer the question, what is the probability that the female scored at least 2 points higher than the male? What combination of the male ACT scores and female ACT scores could help us answer that question? So think about that for a second. And the answer is we would need to subtract the two distributions so we can see the difference between the two ACT scores, and we can determine how often or what probability have the female 2 points higher than the male when we figure out that difference. So this is a problem where we're subtracting two random variables. So we want the new distribution, we'll call it Z, to be the female ACT scores minus the male ACT scores. Now notice we subtracted it in that direction because we're looking for when the female scores are 2 points higher. To be honest, you could subtract it the other direction. You just have to be careful to make sure that then your new distribution, you know which direction you're looking at for the probability you're looking for. But this tends to make more sense to do female scores minus male scores since we're looking for positive values and female scores above the male scores. So if my distribution is Z equals F minus M, what is the mean and standard deviation for my new random variable Z? So we follow the rules, the same rules we've been following, and my new mean, mu, of z is equal to the mu of f minus the mu of m. So it's 19.6 minus 19.2, which is 0.4. So this is the mean of the differences of the female and male distribution. So they're not that far off. Like we said, the means were really similar. But let's see about the standard deviation. So invoking, once again, our friend Sean Bean, don't forget that one does not simply add standard deviations. That's not how I find the standard deviation for z, nor does one subtract them. We have to go straight to the variances. Well, we weren't given the variance in the problem, but if we square the standard deviations that are given, then we can use the formula for variance. So the formula says sigma squared of z is equal to sigma squared of f plus sigma squared of m. Notice I'm still adding variances even though I'm subtracting the random variables. So I plug my items in for that, and the sigma for females was 2.3 and the sigma for males was 4.1. But I have to square both of those to make them variances because they were standard deviations to begin with. So I square them and add them. Using proper order of operations, you always square things before you add them. So I have to square them first, then add them, and I end up with a variance of 22.1. So I'm still not done because I need my standard deviation, not my variance. So then I go ahead and take the square root of that value, and that gives me my standard deviation of my new distribution z. Now I can go ahead and start trying to solve this problem. So I have this new distribution that is normal because the original female and male ACT scores were normally distributed. And I have a new mean of 0.4 and a new standard deviation of 4.7. So here's a picture of my new distribution, and that distribution represents every possible difference taken. If I took all possible female ACT scores and subtracted all possible male ACT scores, this is all the different possible combinations and what the distribution would look like. So I have this distribution. Here's a question. On this distribution representing differences of female minus male scores, what do values greater than 0 mean? And what do values less than 0 mean? So take a minute, pause the tape, and just contemplate that. Think about this. So what do values greater than 0 mean? And what do values less than 0 mean on this distribution? Well, if z equals f minus m and that number is greater than 0, that means that the female ACT score has to be higher than the male ACT score. So we're talking about if I chose one random female and one random male, if I subtracted their two ACT scores and got a positive number, then that particular random female's ACT score had to have been bigger than that particular male's ACT score. So that's what it means when I have values greater than 0. So conversely, when I have values less than 0, that means that that random female's ACT score was lower than that random male's ACT score. But that's actually not going to help us answer the question we need to answer. The question we need to answer is, what is the probability that the female scored at least 2 points higher than the male when I chose a random female and a random male? So we're going to look for where 2 is on our graph. So now I have this graph and I find 2 on my graph and I think about this question. If I want to know the probability that a female scored at least 2 points higher, then that means I would want to look at the values of 2 or higher on this particular normal distribution. So I can do that a couple different ways. The first way we learned last chapter was to find the z-score. And then after I find the z-score, I can look up the value on my table. And since I want greater than, I'd have to subtract that value from 1. But now we also know how to use our calculators a little bit better. So you can just go ahead and give your calculator a calculator command, or Desmos does a really good job of this as well. So if you did it in your calculator, the calculator command, remember, is your normal CDF, C standing for cumulative, because I want an area, not just one probability. So a cumulative probability, I give my lower bound, which in this case would be 2, and my upper bound, which in this case would be technically infinity, but your calculator doesn't like infinity, so we put a bunch of 9s in there. And then whatever your mean and your standard deviation is. So what our calculator command should look like is this. We have the normal CDF, lower bound is 2, the upper bound is infinity, or 99999, mean is 0.4, and standard deviation is 4.7. And 0.4 and 4.7 are the values we got when we used the rules for combining two random variables. And I end up with an answer of 0.366, which makes sense because 2 is higher than the mean of 0.4. So I would have less than 50% in my probability, so 0.3667. So to interpret this, I would say the probability that a randomly selected female scores 2 points higher on the ACT than a randomly selected male is 0.3668, or about 36.68%. And we'll leave you with this. Love letter from a statistician. You're 3 standard deviations above the norm. Have a great day.